starting. Number 12 in the homework. Oh, it's a method of initial rates.
All right, number 12 is A plus B yields C plus D. 3 experiments are done. And they just change the initial concentration of A, B, and then determine the initial rate. So this is just the starting concentration here.
0.5, 1.5, 3.0. Those last two. So 1.5, 3. Then we look at the initial rates. 4.2 times 10 to the minus 3. Okay, it would be 0.42 times 10 to the minus 2. I'm going to change this.
More for a second.
1.3 times 10 to the minus 2. And 5.2 times 10 to the minus 2. Actually, this is taking time to work this.
So what they did was they kept this the same. So B, there's no change here, but over here they tripled A, and then you look at what happened to the rate. You see what happened to the rate? The rate tripled too, and so that means it's going to be first order in A. So the rate is equal to K A the first, because if we triple it, has an impact on the rate. Okay, then we have to figure out what to do about B. And so B here, they doubled the B. They doubled B here, but they also doubled A. And so if we double B and double A, what happens to the rate? It went up 4 times. And so in other words, we would have 2 times to the, what power is this? This would be the m power, which we already figured out is 1, times 2 times, this would be to the n power, is equal to 4 times. This x is not, I should get rid of it, actually. And so n must be 1. And so it's got to be first order in B. It's first order in both A and B. And then what we have to do is we have to calculate K. And so we come up with a table here, another column for K. K is going to equal the initial rate divided by A to the first, B to the first. And so we get K for 1, K for 2, K for 3, and then we take the average K. And then plug it in up here. And that would complete our rate law.
Is that okay? For that? Okay, other questions? No other questions?
All right, we could figure out M and N, and K experimentally like this, but we were talking about theoretically. How could we figure out what these are? And it turns out it's easy and hard. Depends on if you know. All right, so we have a generic rate law. Rate is equal to K, A to the M, B to the N, etc. Okay. M, N, etc. This is the molecularity. Of the key collision. The key collision is what we call the rate determining step. It's the slowest collision. And so when we're looking at a reaction, A plus B plus dot dot dot, this goes to product. This may be multiple steps or maybe a single step. We don't know. Single or multiple. Steps. The mechanism for the reaction would have it all detailed out. And so you must know the mechanism. So the mechanism would spell this out in terms of individual collisions to get the product. We call these simple or elementary collisions or processes. And so a reaction is made up of a whole bunch of little collisions that are occurring here. And if we look at these simple collisions, then the order is very easy to determine. So we have different kinds of collisions. We have something called unimolecular. How can you have a single molecule collision? Is it even possible to have a single molecule collide? What do you think? Yeah, a unimolecular collision either collides with the wall or it collides with an inert molecule, particle. Something that it's not going to react with. But what happens is when it collides, there's transfer of energy, kinetic energy to potential energy, which could break bonds or is activated. And so here, if something's unimolecular, then the rate for this is going to depend on the rate constant times A to what power? Well, if I double A, what's going to happen to the number of collisions? Will the number of collisions not change? If I double the amount of A in this container, will the number of collisions not change? Double or quadruple? It's going to double. And so if we double A and the number of collisions doubles, then the rate should double, and it should be first order in A. And so something like this, we just have A goes to dot, dot, dot. Just A. Then we have a bimolecular. Bimolecular is something like this, A plus B goes to whatever. And so the rate will equal Ka B. But what would the order with respect to these be? So if I double A, what would happen to the number of collisions? The collisions should double. If I double B, the number of collisions should double. And so that means that this should be first order in A and first order in B, and what order overall? Second order overall. That's if I have hetero molecules or atoms. What if I have the same, like AA? So an A collides with an A to yield something. Then the rate will equal Ka to the, this has got to be second order in A, because if I double A, then both the left A and the right A double in number. Therefore, the number of collisions should double for each, which means it quadruples. That would be bimolecular. And then we have like a trimolecular. Which would be A plus B plus C. Something like this has a lower probability. Much lower probability than like a bimolecular or a unimolecular, because it has to be coordinated so that these three molecules collide at the exact same time. Which, how probable is that? This is what I was talking about, the sandwich. B sits there, and A and C sandwich B, or in some way they got to collide, and so it's going to be a lower probability. But nonetheless, the rate would equal Ka. What order would it be with respect to A? Have to be first order, B first order, and C first order. And then we have variations, A plus B. This would be A squared B, right? Equals K A squared B, and etc. So the problem is we can't tell. For example, if I look at methane, CH4 gas plus 2O2 gas yields product. Is this a simple collision or something more complicated? You can't tell necessarily by looking at it. Right? And so, in other words, does this occur in one step? If it occurs in one step, then we call it a simple, or, what's that other word? Simple or elementary process. But if it occurs in multiple steps, then it isn't necessarily going to, if it's a simple or elementary process, then the rate is simple. The rate is equal to K. It's going to be first order in methane, and what order in O2? Second. But if it occurs in multiple steps, then we don't know. Because this is just the overall reaction. The overall reaction stoichiometrically is 1 mole of methane and 2 moles of oxygen. And so what we have to do is, if this occurs in multiple steps, we have to find the slowest of these steps, because the slowest step will dictate the reaction. And so if it occurs in multiple, then we must find the slowest step and determine the collision in rate law. Because the rate law for the slowest step equals the rate law for the whole reaction. And so, in a way, it's easy. It's easy because if you know what the collision is in the slowest step, then you can get the rate law very simply just by looking at this. Because if you notice, when we have an elementary process, like this, if this is an elementary process, then the rate law is a little bit different because the rate law is going to look like this. AA plus BB, dot, 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 that goes to product. If this were an elementary process, then the rate is equal to K, A to the little a, B to the little b, etc. But we don't know. The whole reason why we use M and N is because we don't know if it's one step or multiple steps. Right? And so, since we don't know for general reaction as given, then we'll just use M and N and try to figure it out from there. So let's take a look at some examples of this. Maybe just your book. We're going to look at some simple two-step mechanisms. Let's use your book's example for right now. Hydrogen plus 2 ICLs yields iodine plus 2 HCl. The experimental rate law for this, let's go ahead and give that to you.
Wait, how common is iodine chloride?
This one?
Yeah.
It's not that rare. It's not difficult to make. These mixed halogen things. Like normally you want an iodine to bond to an iodine, but rather than iodine bonding to an iodine, you can bond an iodine to a bromine or something else. And so you have things like this. Bromine chloride, which it's just a big bromine atom bonding to a smaller chlorine. So the sp3 sigma. All right, this one here, from experiment, the rate law was determined as K H2 ICl. So could this happen in one step? No, it can't, because if this were one step, then it should be ICl squared. We need these three molecules to collide in sync. And so this means that it cannot be one step. And so that means there's multiple steps here. And so what kinds of steps can we have? Well, we can have unimolecular, bimolecular, trimolecular. It's not going to be trimolecular because it's like most obvious trimolecular collision is not going to happen here. And so what do you think? Well, in the slowest step, we need an H2 to collide with an ICL, it looks like, right? The slowest step. Uh-huh.
How do you know that's the slowest step? What do you determine the slowest step?
Because the rate law is always equal to the rate of the slowest step. We just don't know what the slowest step is. I mean, that's where, M and N come from this, the M and the N. Apparently in the slowest step, it looks like an H2 collides with a ICL. So in fact, let's just do that so maybe we'll do that as step 1. An H2 collides with an ICL. This would be first order in H2, first order in ICL because it's just a one-to-one collision. What forms though? An H2 collides with an ICL. What would form? Yeah, probably an HI and an HCl. Something like that. That seems reasonable, doesn't it? You want to form some reasonable stuff, but if you look, HCl is fine, but HI is not present. But that's okay, because HI we call an intermediate. An intermediate will be consumed by the time we end this reaction here. Well, we need to get rid of that intermediate HI. What do we have left over to react it with? An ICL. And so if we take an HI and an ICL, it's going to form a I2 and an HCl. And so now, if you look at these two steps, if we add up step 1 with step 2 of the mechanism, we're going to get this. It's going to be an H2 plus 2 ICLs. The HI cancels, intermediate. This is going to produce I2 plus 2 HCLs. And so this could potentially just consist of one simple 2-step mechanism like this. This is the net reaction here. Now, the two things. One, the sum of the steps of the mechanism has to equal the net reaction, which it does, step 1 plus step 2 there. And 2, the rate law of this must equal the experimental rate law. And so if we look at step 1, what is the rate law for step 1? The rate law for step 1 is K H2 ICL. Do you see that? And so if we call the first step slow, we just say that this is the slow step. The slow step is called the RDS. RDS stands for rate determining step. The slow step is always going to be the rate determining step. And so if we call the first step the RDS, then everything looks good. It doesn't matter. You know what? It doesn't matter how fast step 2 goes. Because it's not, as long as it's faster than step 1, it's not going to inhibit the reaction. It's not going to slow down the reaction. Yes?
Is the rate or the slow step always the first step?
No. It's not always the first step. The slow step is what they call the bottleneck. It doesn't matter how fast you can go. Like the example they give is, it doesn't matter how fast you can go on the freeway. If there's a bottleneck, everybody's going to be going the same speed. Once they hit that bottleneck, right? And so it doesn't matter how fast before or after you go, the rate is always going to be determined by the bottleneck, which is going to be this step. And so we don't need to know the rate for this. We just need to know the rate for this. And the rate for this is just, it's a simple collision, right? That's all it is. This is simple collision. Let's talk about simple collisions now. In a simple collision here, we usually map out the collisions. Energy and what we call reaction progress or reaction profile. So this is a slow step here, and so what's happening is this. I don't know energetically which one do you think is lower in energy? What kind of reaction is this? It's a redox reaction. And so what's the reducing agent? What's the oxidizing agent here? Yeah, H2 is the reducing agent, and ICl would be the oxidizer. And the way we do the oxidation states here is, you want to, which one do you assign first, iodine or chlorine?
Most electronegative.
Most electronegative, which is
Chlorine.
chlorine. So chlorine gets its normal charge, -1, which means iodine is +1. And so hydrogen's 0. And so what's going to happen is hydrogen's losing. Who's it losing to? Iodine. And so we got two hydrogens. And so iodine goes from +1 to 0, and then from 0 to +1. I'm sorry. From +1 to 0, and then 0 to -1. So just a redox reaction here. Which one do you think is higher in energy? The reactants or the products in this case? The reactants. And so we'll just put it up here, reactant. And the reactants are going to be hydrogen and ICl. And then the hydrogen and the ICl have to come together in a collision. In order for a collision to be successful, there are two things that a collision must have. A successful collision must have the correct orientation. And so, take a look at what we want to form. We want to form HI and HCl. So how do you want to collide these two? You probably want to collide them side on. If you collide them head on, right, you might form an HI or HCl, but the other part might not form. And so we'll have a side-on collision. In order to get that correct orientation, then that means if you take 1,000,000 collisions, what fraction of those collisions do you think will have the correct orientation? A large fraction or a small fraction? A small fraction, because they're going to be oriented in lots of different ways. Not only that, are they going to be coming straight at each other? No, they might be traveling in the same direction and collide. This. And so there's so many different collisions, and they're totally random. And so out of all those random collisions, how many are perfectly oriented like this and moving at each other? Right. A very small fraction. And the other thing a collision must have is the energy. This energy we call E sub A. E sub A stands for the activation energy. Activation energy, sorry. The activation energy we represent like this. So this is an energy level diagram. And so we plot energy on the y-axis. And then what we do is we draw this going up, because the collision, it has to be energetic enough so that bonds can be broken and new bonds can be formed. And so what we end up with is here, where a new bond is being formed between the H and the I, and a new bond is being formed between the H and the Cl. And the HH bond is breaking, and the ICl bond is breaking. This is called a transition state. It's just transitioning from the reactant to the product here. And you know, you don't capture this. This is not stable. I think the products are going to have a lower energy here. And the products are going to be HI and HCl. I didn't even write out the lone pairs. I should. So that's a little lower in energy here.
Do reactants always have to be higher in energy? Or
No, reactants could be lower in energy as well. But the activation energy is just from where the reactants are to here. So this is the activation energy. This reaction is reversible too. You know, you could have a collision between these and go backwards. But if you look, what is the activation energy going backwards? It's a lot larger. You know, there has to be a much more energetic collision to climb up here to form the transition state and then drop back down to reactant. And so it is reversible, but the activation energy is different. If the activation energy is different, then the rate is going to be different. All right, then we have to add in our other ICl here and have another collision. We're going to have the ICl collision with the HI. And so it doesn't matter how fast. You know, the ICl and the HI, we're going to say this is a faster reaction. It's a faster reaction because maybe it doesn't require as much energy to break the bonds. It has a much smaller activation energy. But it doesn't matter how fast this, you can go over this little hump here, because the rate determining step will be that, the first one. And then that'll slow everybody down. And then we'll go to products here. So this is a two-step reaction we can kind of map out like this, where we're going to get I2 and 2 HCl. So over here, you know, in the second step, it would be first order in HI and first order in ICl. Do you see that? And so we can see how M and N are going to vary. But let's take a look at K. Where does K come from?
And K is called the Arrhenius equation. We have different forms for the Arrhenius equation. Let me see. Sometimes they call the constant different.
A e to the minus e sub a over RT. This is the Arrhenius equation.
And so that's where it comes from.
A is called the frequency factor.
Now, a frequency factor is how frequently or how probable are those collisions. You know, the more frequent those collisions, the more frequently those collisions occur, the bigger the A, the bigger the rate constant, the faster the reaction. And then E sub A is the activation energy. And so this term here, minus E sub A over RT, where does that come from? That comes from this. You guys remember what a thermal distribution looks like? In terms of population versus, well, let's see, population versus energy.
Maxwell-Boltzmann.
Yeah, right. The Maxwell-Boltzmann distribution, what does it look like?
Bell-shaped with a tail.
Yeah, bell-shaped with a tail. Now, do all these have enough energy? No, it turns out that only a limited number of those have enough energy. And that limited number will be the ones with an energy greater than E sub A. And so if this is my E sub A, then this population has enough energy to react potentially. Right? And so what E to the minus E sub A over RT tells us is how this population changes with activation energy. You know, the smaller the activation energy, the bigger the K, right? The more the collisions. The bigger the activation energy, the smaller the K. This is inversely proportional. And then temperature. You know, the larger the temperature, the higher the population. The smaller the temperature, the lower the population. And so mathematically, this is given by this right here. It's just an exponential function. And so how do we figure out things like the collision frequency A, theoretically? Theoretically, you would do some, probability, some statistical analysis, looking at all these random collisions, and then seeing what the probability of the likelihood of that is. And then, how would you do this, And so A, let's look at, experimentally versus theoretically. A, you'd look at statistical analysis, of collisions. And B, E to the minus EA over RT. EA, how would you determine EA? What would tell you EA? What would give us the energy? The energy of what? If I wanted EA, I need to know the energy of what? EA is the activation energy, but I would have to know the energy of what in order to determine the activation energy. It's not just the bond strength. If it were just the bond strength, then I could just look in chapter 9 or chapter 10 and get all the average bond energies, right? It's a little bit more because not only are we breaking bonds, we're also forming bonds at the same time. So it's a little bit more tricky. And so to determine EA, you would use, theoretically, you would use some quantum mechanics computing program. Yeah. And then what you do is you just model. You know, you build a little model of the transition state and then ask it to calculate what its energy would be. And so from this, you model the transition state. Then calculate its energy. That's theoretically. Experimentally, we could get this stuff too. The way we get A and E sub A experimentally is either two ways. The best way is probably to do an Arrhenius plot. What is an Arrhenius plot? Well, what we do is take the natural log of both sides of this. And so if we have k, ln of k equals ln of a e to the minus e sub a over rt, and then we do some simplification of this, right, using the property of logs. So we'll just get ln of k is equal to, okay, it's going to be minus e sub a over r, that's a constant, times 1 over t, which is a variable, plus ln of a. Okay, when you look at this equation, what form does it have? Well, it has the y equals mx plus b form. And so what would we plot here? What we do is we make a table. We measure the rate at different temperatures, the rate law. I mean rate constant at different temperatures, right? You know, usually when you increase the temperature, K should increase as well. And so we have the K versus T, and then what we'll do is we'll take the ln of K and plot that versus 1 over T. This. We generate a plot. And so we just collect the data. And it should be a straight line. The slope of this is equal to what? Slope is minus EA over R, and then the intercept here is ln of A. And so from the slope and the intercept, we can calculate EA and A. This is good because if we have a lot of data, you know, we could do a linear least squares fit, which would average everything out. But how many points do you need to define a line? A straight line? 2. All you need is 2 points to define a line. And so this is a multi-point analysis. You could do a 2-point analysis the exact same way, right? Or you could use a simplified equation for just a 2-point analysis. Which is something we do a lot. This 2-point analysis is, since we do this a lot, I'm going to write it out. What we'll do is we'll take ln of K at temperature 2. We'll just call it ln of K2. Minus ln of K at temperature 1. Okay, this is going to equal, well, ln of K2 is equal to minus EA over R, 1 over T2, minus a minus EA over R, 1 over T1. And then we just do some simplification of this. This is going to be ln of K2 over K1 is equal to, and I'm going to factor out the minus EA over R. And so it's going to be minus EA over R, 1 over T2 minus 1 over T1. This is a two-point analysis. What this does is this. What this does is it allows one to determine the activation EA, activation energy, from 2 data points. The data points would be the rate at a given temperature, the rate law at a given temperature. Or it allows us to determine K2 at any temperature given EA. So this one's handy, except it's just a 2-point analysis, so it's nicer to have multi-point data. So just you aren't subject to random error. One of the things, when I'm talking about a ratio like this, K2 over K1 is going to be, proportional to the rate of 2 over the rate of 1, which is going to be proportional to the time. How is this proportional to the time? Well, if something has a fast rate, then it should have a short time. And so this is going to be proportional to the time, like this. T1 over T2, the time of reaction. And so what we're going to do is this. An old rule of thumb, if we have a plus 10 degrees C temperature increase, then the rate doubles. What must be its activation energy? And so let's pick a temperature. We'll go from 80 degrees C to 90 degrees C. Cooking something in warm water. Determine the activation energy. So why don't you guys try that? I'll be right back.
Did you get it?
Yeah.
Yeah? What did you come out with for the?
40.95, but I'm not sure what it has to be true.
Yeah, the units of this would be in
Joules?
Those are kilojoules.
Well, the thing is, R, what did you use for R?
0.082.
8.31
Okay, R should be 8.3145 joules per mole
Kelvin.
Kelvin.
And that's wrong.
Then, yeah, okay.
This is 5,720.
5,000?
720.
5,720, so 5.72
To kilojoules.
kilojoules. 5.72 kilojoules.
Is it per mole too?
Yeah, per mole. Is that what you got?
No.
No? What did you get, man?
The 412.
412?
46.
412.6 joules? 412.6 joules per mole. What did you guys put in here? 2. You know, 2 over 1, so just 2. And then T2, did you convert that into Kelvin?
Yes.
And T1 converted into Kelvin? Okay.
I just did do the math first and I convert it. So I do 1 over 2.
No, you can't. You have to convert it first.
Oh, okay.
Because if it's 0 degrees C,
Oh, okay.
then it's going to really screw things up.
Okay.
So, all right, for 412.6, this rule of thumb, where did it come from? The rule of thumb came from cooking. And so people thought, well, if you cook it, for every 10 degrees C temperature increase in cooking temperature, it cooks twice as fast. But when you think about it, it's just going to be for very limited applications because look at this energy, 412.6 joules. Is that much energy per mole? What is a bond usually? A hydrogen bond is about 25 kilojoules, right? So this seems awfully small. So this is probably just denaturing proteins or something like that. And so it's quite small. So for a typical chemical reaction, you wouldn't see a doubling of the rate with just the 10 degrees C temperature increase. You'd probably see much more because in a typical chemical reaction, the activation energies are bigger, in the kilojoule order, right? Joules. Well, anyway, that's a little bit of theory. Not theory, what did I do? We talked about, K, theoretically and experimentally, and then just an application of K here, just one application. But this is what we're going to do in our for mechanisms. We aren't going to determine K, for our mechanisms. And so in the last mechanism we did in that two-stepper, the only thing we'd say is this. We would have stopped analysis there and said the mechanism is consistent with experiment. But it doesn't prove that mechanism because other people might come up with different mechanisms, different collisions that might yield the same rate law and the same overall reaction. But to prove this mechanism, more experiments required. One of the experiments would be to do what? For example, we try to detect the presence of the intermediate. What was the intermediate in that case? HI. Etc. And so if HI was detected, HI doesn't live forever because it's going to be consumed, but it lives much longer than a transition state. And transition states are inherently very unstable, whereas an intermediate has some relative stability. And then it undergoes the further reaction there.
And so if you could try to prove prove that. And so there are other things, other data you need to know. Now, is the first step always going to be the slow step? I'll tell you, it would be nice if the first step were always the slow step, because then your life would be much easier. You wouldn't have to worry much about the other steps. But there are reactions where the first step is not slow. And so let's take a look. We're just going to use your book, and then we'll look at something more complicated maybe. This is the book's example here too. It's going to be 2NO plus O2 yields. Look at this yield. I think you can figure it out. 2NO 2. Okay. The rate law from experiment. Experiment always is true because it's just experimental fact. Theory, however, doesn't necessarily. I mean, if the theory does not match the experiment, then there's trouble, right? This is why theoreticians are very interested in the experimental data, because they want something to confirm their theory. And so this is K NO squared O2. This is from experiment, and so when we look at this, it looks like it's one step, doesn't it? It's possible it's one step. And so one mechanism it's consistent with would be a one-step mechanism. If this were a one-step mechanism, then this would be the net, and this would be the rate law. Does everybody see why that would be the rate law? This one step? Yeah. And so one-step mechanism is consistent with experiment, at least up to this point. And so we'd say it's consistent, but the probability of this is low for a trimolecular. Trimolecular is also called termolecular. In fact, it's more commonly called termolecular. It has low probability, therefore you would expect the reaction to be somewhat slow or slower. But this is a fast reaction. A very fast reaction. NO is a product of when nitrate and, like when nitric acid reacts. Nitric acid reacts as an oxidizing agent. NO is usually produced. NO is a colorless gas. But the NO is oxidized by O2 and air, and it makes a brown gas. And this brown gas is immediately visible when you use NO to, when NO is produced. And so what this means is it might not be a termolecular. Can we think of another mechanism that involves more highly probable collisions? So it might not be her molecular. Well, let's try to think of an alternate mechanism that requires just unimolecular or bimolecular. And so can we think of an alternate mechanism? Can we think of an alternate mechanism with uni or bi? Actually, let's go with bimolecular. Bimolecular collisions seem pretty probable. It doesn't have to be, but we'll just go with bimolecular right now. And so what are the choices for bimolecular collisions? And so we have some choices. We could have an NO collide with an NO. Or we could have an NO collide with an O2. Which one do you want to do?
NO plus O2.
Actually, it doesn't really matter which one we do. We could do either one. An NO plus O2, what would that form?
NO2 and O minus.
Okay, NO2. It can't form an O minus because the charges have to balance. Do you see the net charge here is 0? The net charge here would be -1. So all of a sudden you have an extra electron that appeared out of thin air, you know, just magically appeared. You aren't going to have that. And so it could be an NO2 plus an O. An O would be called atomic oxygen. Atomic oxygen is what we call a free radical. You know, when we look at the valence electrons, it has 6, so it wants 2 more bonds, right? And so it's highly reactive. It's called a free radical. NO2 is interesting too, because NO2, N has 5 electrons, and plus the 2 oxygens, which would be 2 times 6 electrons. So 5 plus 2 times 6, this gives us 17 electrons. NO2 is a free radical also. It's a free radical, but you know, has a odd, anything with an odd number of electrons is what we call a free radical. Free radicals are unstable because they have that odd number of electrons.
So how is the charge neutral on
How's the charge neutral on NO2?
It has extra electron flow.
Yeah. The charge is a result of the sum of the formal charges. All the formal charges are 0 or the sum of the oxidation states. The oxidation states here, you know, you got -2 for this oxygen, you got 0 for this one, and you got 1, 2, 3, 4. It's supposed to be, did I get this right? 2, 4, 6, 8, 10, 12, 14, 16, 17. So 2, 4, 6, 7. I'm sorry, -1. 1, 2, 3, 4, plus 1, and 0. That's how it comes out to 0. Oops, I didn't do it right, did I? I did formal charge. I circled formal charges. These are the formal charges here. The oxidation states will have to give us the same result. I'm getting mixed up. The oxidation state of this is -2. The oxidation state, this only has 1 electron, so it's plus 4. This is -2. And so, yeah, either way you look at it, some of the oxidation states or some of the formal charges has to add up to the net charge. That's one possibility. We could have this, or if 2 NOs collide, what do you think you'd form? 2 NOs collide. You know, well, if 2 NOs collide, you might form N2 and O2. What do you think? Maybe, but N2 and O2, once you form N2 and O2, that's like forming air. And air, is it very reactive? No. So I'm not thinking N2O2. This doesn't sound so good because this is kind of stable, as we know. And so it doesn't look so promising. What else could you form if 2 NOs collide? Maybe you could form maybe nitrous oxide plus a free radical, oxygen, right? That might be. Or you might form N2O2. Have you ever seen N2O2 before? It was in one of the earlier chapters. Maybe it was N2O4. So these kinds of things look promising. But you wouldn't form things like this, you know? Would you think you'd form maybe N3 minus, N3 minus, O2 minus, O2 minus? You think you'd form something like that? No, this is impossible, right? Because of the charge screwed up. So that's for sure impossible, but all these others are possibilities. So which one looks good to you? N2O2? All right. So if we do as step 1, let's just do this as step 1. NO plus NO yields N2O2. Then what is the rate of step 1? Rate is going to equal KNO squared. So this cannot be the slow step. This can't be the slow step. In other words, it can't be the RDS. And so what we have to do is we'll take the N2O2 and react it with what's left over. We haven't used our O2. And so in step 2, if we take N2O2 plus O2, this gives us 2NO2. And then what is the rate of this? The rate is equal to K, and it's going to be first order in N2O2 and first order in O2. But when we look at this, we can't have an intermediate in our rate law. It's hard to, let's say I wanted to double the intermediate concentration, it's hard to do that because we aren't adding it. And so this is what we're going to do. We have two approaches we can take for this. We can do the fast reversible, or we can take the steady state. For the fast reversible, we assume that step 1 is fast and reversible. And so what that does is this. We're going to have what we call a K1 and a K minus 1, or a K2. Well, I'll call it K minus 1, and this will be K2 here. And so what this means is that K1 is equal to, actually, let's just do this. The rate of the forward is equal to the rate of the reverse. That's what we mean by reversible. It's just kind of this equilibrium situation. The rate of the forward is equal to K1 times the NO squared. The rate of the reverse is equal to K minus 1 times the N2O2. And then we solve for N2O2. The N2O2 concentration is going to depend on the NO. Second order. It's going to have a second order dependence on the NO. And so the N2O2 intermediate concentration is going to equal K1 over K minus 1 times the NO concentration squared. And then what we're going to do is we're going to substitute this back into our rate law here. And so this is rate for step 1. We'll go back to step 2 here. The rate for step 2 is equal to K. All right, now this is step 2, so this is going to be K2. Or this K1 here. It's going to be K2 times the N2O2. Well, the N2O2 is just this. It's going to be K1 over K minus 1 times the NO squared. And then it's going to times the O2. concentration here. And so what we're going to do is we're going to combine these constants and just call it K prime. It's going to be K prime NO squared O2. And so this is the rate of step 2. If I look at the rate of step 2, this matches the experimental rate law. Well, it matches the experimental rate law. Therefore, what can we say? Well, we would say this, that step 2 has got to be the slow step in this mechanism, and that this rate law is, because does the net add up? Does the intermediate cancel? Yeah, we get 2 NOs and an O2. Gives us 2 NO2s. And so the net matches, and the rate law matches, correct? And so we can say that, well, that was a good choice for first step. It appears to have been a good choice, right? But what if I didn't pick that one? So this matches, it's consistent. But what if we started with this collision? The same thing, NO plus NO. But in this case, let's go with maybe nitrous oxide plus free radical oxygen. If we did this, would we get the same rate law? Or how about this? No. What if we did this, NO plus O2, and this yield NO2 plus O? Would this have yielded the same rate law? So if we did this, or, if we did step 1 like this, and then step 2 like this, step 2 would be getting rid of the intermediate O. And so that would be O plus NO yields NO2. When I add these two steps up, it looks like it matches. And then we're going to call the second step slow. If we call the second step slow, actually, I'll stop here because I'm out of time. Would we get the same rate law? Is this one also consistent? And so try it and see. Okay. I'll stop here. But we're not quite done with this chapter yet, chapter 14 yet. Tomorrow we're going into the computer lab, so let's just meet in the computer lab. Okay. Bring your data tomorrow so we can plot it out. We're going to plot out both the titration and the CV kinetics lab. You could try it. Somebody said they do.
So, Professor, I had a question. So when we're doing this part, why did you cancel K2?
Oh, no, K2 and K1 is equal to 2 over 1. That's what I meant.
So this is equal to 1, right?
No, equal to 2.
K2 is equal to 2?
And K1 is equal to 1.
Okay. And why is that?
Because K2 is twice as fast. K2 is twice as big as K1. So K2 equals 2 times K1. And K1's cancel.
Yeah, well, why would that be?
Because I said rate double.
Oh, because you gave us the double. Okay. That makes
double.
Thank
The
you.
computer lab we're going to is just the one in that building right
No,
there?
this building.
Here, okay. What room number?
Chem 108.
Okay, thank you.
Number 12. The 2 that goes into concentration, where is that 2 coming from?
Oh. No, I'm just saying, okay, we doubled it
Right.
here, and so that's 2 to whatever power. And we double it again, so that's 2 to whatever power.
Okay.
And so and then the rate increased by 4-fold.
Well, but right here we triple it, right?
No, I'm taking the second 2. This 1.5 to 3.
Oh, you're taking the second 2.
Yeah.
Okay.
From 1.5 to 3, it's doubled.
Okay, right.
And so if we double this, it's first order in A, we should double the rate, but the rate quadrupled.
Mhm.
And so this has got to be, so we doubled this, then it's got to go up twofold again. So it's got to
Okay.
be first order.
And we determined that this one is first order from the first,
Yeah,
two,
right.
okay. So then, if this is tripled here and the rate is tripled, how come it's, so I guess I'm asking, why is it first order then? What makes that first order?
Oh, because whatever you do to the concentration, first order means you do the same thing to the rates. So it's directly proportional.
So it's directly proportional?
Yeah.
And second order means, so if I take,
If you triple the concentrations, then the rate should have went up 9 times.
Okay.
Second order. The second order would be square.
so first order means whatever I did to concentration, same thing happened to rate.
Yes. Aye.
I have a doctor's appointment today, so is it okay if I leave like 5 minutes before class?
Yeah, that's no problem.
Are you in 1B? Nice. Dang.
Yeah.
Wait, so is chapter 14 going to do this week, or are we doing chapter 19?
In our class, he hasn't finished lecturing on it yet, so I don't think it's due yet. I think there's a test this week on it.
Yeah.
Probably due next week.
Okay, cool. Test next week, alright. Very nice.
Love.
What's up, dude?
Yo,
It's good.
nothing much. Got a doctor's appointment today. About it. You?
Just regular checkup or what?
Regular check. Did a physical.
Right on, dude.
You? Anything happen on the weekend?
Just work.
What do you want, guys?
Check, dude.
Check them up. You? Fucking close, dude. Serious.
On taking management?
It's crazy. It's so packed sometimes. Literally yesterday, within like the span of 20 minutes, I think we had like 20 people at once come in. It's just people get pissed, people start yelling at you and shit.
The retail told me about that.
What?
Retail told me about that.
Oh, what do you work?
I used to work as an arm tech with like airlines.
Oh, really?
For the last 2 years.
What do you mean out of farm tech anymore, dude?
Going to college, man. Gonna be a pharmacist.
Right on. Oh, yeah.
Getting that work experience in the industry. They've application is good.
Who is your pharmacy?
3 months ago, after like undergrad, you do like 4 years.
Oh, is it?
And then you take your test by the California lecturer. She said, oh yeah, you're smart enough, you passed, so there you go, you're a pharmacist. And you just go back to Walgreens.
I get paid.
Except I'm the boss. You passed, I don't know. I work with my mom's sister. Yeah, my mom. Yeah, she's still. She's a pharmacist. I was like a pharmacist like 3 other days. She made what she does. She's still very funny though. They have the like 16, yeah, 15, 16 about. So how long you do. But still, you take like a test.
You have to like go to school for like a year now.
It's just a test. There are 3 ways. Either one, you go to the army way, right? You go to the school way because you go to Alcoa, you do 2 years, 2 years you should, and then you get a job after that. Third way, you take a licensure exam, the PTCB. Get your license. But the thing is that if you go with the Alcoa way or the 2-year college way, is that you kind of have like a built internship so you can get hired right after. I was lucky because, I'm like related.
It's always easier when you know someone right on. I used to work.
They can vouch for you. Yeah. Like, my little nephew is pretty cool. He's kind of hardworking. He's competent.
That's one way to put it, dude. Yeah, I used to work in computer technician, and I used sometimes only reason I got the job.
Like IT stuff, like Central Wi-Fi or...
Yeah, like IT, I used to work for another school.
Where at?
I was in school.
Slow?
Yeah. Went to school after a while.
Came by Delta?
Yeah. That's pretty nice. I just stick around, play like Finding Devices, Steam games, I just get paid for Steam games. Because unless someone called in, I didn't have anything to do.
I am
It's so much more sick. It's more smooth too. Because the first one was like
the firing mechanism back in the first one was like so cool. Like, spray and pray.
Well, it's also because it was.
I think this thing wasn't there. I think they used to use Chem.
Yeah, because it was a flash game before. And the flash changes.
But now they're doing like an Unreal Engine thing.
It's a little more smooth, and before, because you were playing with flash, it was super like laggy.
I know, like going from like one room to the next room, it's like, wow, and then they do
Yeah, they cleaned it up nice.
So dude, how's math? How's math?
Calc.
In general.
The last test? I tried to get like the class I was
No, you didn't? I did it 2 points over. 2 points over, 36.
Oh, okay, that's good.
Yeah, like, I really think that you should have given us like an exam with visual bar. You know what I'm saying?
Oh,
Like, you're on the first, like, I won't like fail the first test, but I would be like half. Yeah. My average right now is like freaking out, like 87. I have to like work hard for the because we're more attention in the finals.
With work, throw myself on the and like never talk to anybody.
well, you said he might do a revision. You said after you correct the
Yeah, you can hear you get them. Like last Thursday, weren't you there?
Oh, yeah.
David, I believe you're my senior.
Nah, man.
No, you're definitely.
No. Today? Let's leave it today. So I'm gonna leave like 10 minutes early anyway. You have it done.
Thank you. You made it.
Whoa, my first one.
So it's possible. It's